So let's pick up where we left off, and that's at about this point in the homework where we're asked to find S, which denotes the length of the arc of circle of radius r subtended by the central angle of theta. Wow. If I asked every one of you what that means, I'd probably get blank stares. This is the kind that I'm getting right now. It's like, what does it mean? So let me help translate that. That's my job, is to help you understand what's going on with this stuff. So basically, what you've got is some angle theta for a circle of radius r, and when you extend that angle out and it intersects a circle, it's going to intersect part of it, and that part of it that it intersects is going to have an arc length, and that little piece in green is what we're trying to find the length of. That length is S. And it's got a very simple formula for that. The arc length is S equals R times theta. So the radius times your angle. Now there's one big catch, and this is where people are going to get this one wrong if they get it wrong. Theta must be in radians. Don't shoot the messenger. I don't make this stuff up. I just teach it. But it has to be in radians. If you do this in degrees, you're going to be way off. So let's do a few problems for this stuff. And we'll start with kind of a friendlier one here. Problem number 72. So r is 6 feet, theta is 2 radians. Now, is there a pi that's part of this for the angle? No. Don't put one in there. This is supposed to be an easy problem. It is. So for problem 72, S equals R times theta. The radius was 6 in terms of feet. Theta was 2. So the arc length is 12 feet. And that's it. Now we were lucky in that one because they gave us an angle in radians to begin with. What if they didn't give you an angle in radians to begin with? What if they said, oh, okay, well, the radius is 2 inches and theta is 30 degrees. Well, okay. Could get something like that. Actually, we've done 30 degrees, so let's practice something different. Let's do number 78. R is 3 meters, so 78. R equals 3 meters. And theta is 120 degrees. Okay, that's a little bit more of an interesting example. So it's my same formula as before, S equals R theta, but I hope you don't give me 360 meters. It's going to be way off. We're going to start by converting that to radians. So 120 times what? Remind me. Jack, what do I multiply by to convert to radians from degrees? Two radians, yeah. So the units I want to cancel out are degrees. Perfect, thank you, sir. Pi over 180. And this is exactly what I want because units of degrees will cancel and I'll be left with, let's just do it this way, 120 over 180 times pi, and that reduces to 2/3. Yay. So that's the number that I've got to put in here for theta when I calculate S equals R times theta. So S is going to be 3 times 2 over 3 times pi. And man, did they hook you up on this problem or what? Look at that. Even the 3 cancels out, and you're just left with 2 pi. So yay. 2 pi. There's a unit missing here, though. That length would be a linear length, and that's going to be the length in meters. Now, if I just ask you for the answer, you can leave it that way. If my math lab asks you for a decimal approximation, you're going to have to take out your calculator and multiply 2 times pi and then round it off to whatever they ask of you. So, nice. Let's go back up to this formula here and add another thing here that we can calculate, and that would be the area. So how much area is in this little wedge here? And the area for that is given by another simple formula. Area is 1/2 r squared theta. Can anyone tell me anything about what you think theta is going to have to be in? Do you think it's going to have to be in degrees or radians? Radians. Yeah. There's just no getting around it. So our area is given by this formula. Let's practice a couple with that. So let's go back over to here and jump down to 1 in radians. So A denotes the area of a sector of a circle radius r formed by the central angle theta. Find the answers to 3 decimal places. Let's pick one that's in, well, we can do this last one. We can do problem number 86. The nice thing about problem number 86 is we kind of already did part of that. So problem number 86 here for us, area equals 1/2 r squared theta. In this case, r is still 3. Theta is 120 degrees. But kind of like the last time, we know we're going to have to convert that to radians. So it's 2/3 pi. All right, let's put that all in there. 1/2 times 3 squared times 2 over 3 times pi. Let's see if we can't simplify that a little bit. That's going to be 1/2 times 9 times 2/3 pi. Going to get a lot of cancellation here, aren't we? Let's try and keep track of it by being clever. Let me cancel out the 2's this way. Those will cancel. What else is going to cancel for us? Yeah, one of the 3's is going to cancel. That's going to cancel and leave me with a 3 up here. So I'll be left with 3 pi. Yeah, looks like everything's canceling. So 3 pi. And we got to be kind of careful here. I think the units here were meters, right? What units are area going to be expressed in? Not just meters. There you go. Square meters. Meters squared. Yep. Perfect. Nice. Now you can also do these kind of problems in a reverse direction. So let's see here. Let's try problem number 81. So we've got the theta is 1/3 of a radian. Theta is 1/3 a radian. The area is 2 square feet. Square feet. And we want to know what the radius is. So we're kind of working this problem a little different direction. That's okay. We can still do that. Let's fill in what we know and solve for what we don't know. So there's going to be 2 here equals 1/2 times r squared times theta, which is 1/3. Now how come I'm not putting a pi in? Well, it didn't give me pi. It just said it was 1/3 of a radian. So the nice thing is that it's in radians, although maybe to our comfort level it would be nice if we had a pi, but we don't. That's okay. 1/3 times 1/2 is 1/6. So this is 1/6 r squared. Personally, if it were up to me, if I was doing this just for myself, I would get rid of the 1/6 by multiplying both sides by the reciprocal, which would be 6/1. So I get 12 equals r squared. Now in an algebra class, you'd probably be asked to give me the plus and minus here. But how come I don't need the plus and minus in this case?
Because you can't have negative area?
Well, r is not the area, but r is the radius, yeah. And you're exactly right. Thank you so much, Sydney. Yeah, you can't have a negative radius, all right? So at least not till later in the course. But when we get the square root of 12, you could write that as 2 square roots of 3. That's your r. I'm not going to bust your chops if you want to write it as a square root of 12. But there is one thing that we do need here, and that is the length in what units. I started out with the area is 2 square feet. What's that telling me about the radius? Is the radius going to be in meters, inches, yards? It has to be in feet. All right. So here was 2 feet squared or 2 square feet. However you want to write it. Linear dimensions, that just has to be the unit to the first power. So the first power, not, units of minutes. When you're talking about area, it's to the second power. When you're talking about volume, it's to the third power. So do pay attention to those little things. It'll help you make sure you don't make any mistakes. And it'll help you also make sure you get all the points possible. Let's play around with our formula a little bit. So going back to our formula, it was this one. S equals R times theta. Whoops. Yeah. People are looking at me like, what formula? Yeah, this one. Sorry. S equals R times theta. And what I'm going to do is I'm going to divide both sides of this formula by t. Now, S for us was length, or you could also think of it as distance. What do you get when you divide distance by time? Distance divided by time is your speed, or your rate, or your velocity. So we'll do V as velocity, which has a magnitude and direction, if those of you who have taken physics. Now over here, I'm going to rewrite this as R times theta over T. I'm just going to divide that theta by the T and then multiply it by R. It's the same thing as I have over here, but I'm going to give this a new name. It's going to be R times, and I know it looks like a W, but neither of these are actually English letters. This is the letter nu, and this is the letter omega. Now, I'm not going to make you, write nu and omega. If you want to write V and W, that's fine. But we need to understand what W represents. So nu, that's your linear velocity. That's how fast a point on the rim of your wheel is moving as you turn your wheel through this angle per unit time. So this is your angle in radians per unit time. Basically, it's how fast is your angle changing in radians. So it's going to take a little bit of you getting used to. It's not something that's intuitive right away. So let's take a look at a couple problems with this stuff. And let's look through. Problem number, let's see which one I want to do. Which one's user-friendly? We will get to 105. I'm just trying to decide if I want to do that one first. Let's take a look at problem number 111. So 111, right there. It says the mean distance of the moon from the Earth is 2.39 times 10 to the 5th miles, about 239,000 miles if you want to take and put your feet on the moon. Assuming that the orbit of the moon around the Earth is circular, it's not, it's an ellipse. We'll ignore that. And that one revolution takes 27.3 days. Find linear speed of the moon. Express your answer in miles per hour. All right. So that second part is a little extra work. That might be an extra credit. It might be part of a problem. But let's work with the first part. So we want to figure out how fast is it moving, its linear speed as it moves around the Earth. So let's write down some of the things we know. Starting out with the radius, R, is 239,000 miles. I'm not going to bother writing it in scientific notation like they do here. I'm just going to write it as 239,000. And the other thing I want is that one revolution takes 27.3 days. So 239,000 miles. That's our radius. And omega is going to be one revolution every 27.3 days. The question is, what's the linear speed? What's omega? Well, unfortunately, one revolution is not an angle in radians. But it's not too far from an angle in radians. Let's think back. What would one revolution be in radians? One revolution would be starting out here and going all the way around. That's one revolution. So what's one revolution in terms of radians? How many radians? 2 pi. Beautiful. So the key to doing this one the right way is to realize that one revolution is 2 pi. So I can write this as, I can write that as 2 pi per 27.3 days. That's kind of nice. So we didn't have to do a whole lot of work there to write that in radians per unit time. Well, that's pretty good. Now to figure out the linear speed, we want to take 239,000 miles and multiply it by omega. So V is going to be 239,000 times 2 pi over 27.3 days. I should probably put in miles here. Keep track of our units. So this looks like a job for the calculator. Let's take that out. Let me clear out a bunch of stuff here. I want 239,000 times 2 pi, 2, and then second pi, divided by 27.3. Wow. That's pretty good. 55,006.6. I'm just going to round it out to 55,006.06 or 6.6. But what are the units? What are the units that we've got here? Well, did any of the units cancel out? No. So the units in the numerator are miles. The units in the denominator are days. So about 55,000 miles per day. Wow. Wish I could put that in my frequent flyer account, man. I'd be taking trips all over the place. Pretty sweet. Now, are we okay on this part? This is kind of like the main part. We are going to go with a little bit further because, I mean, miles per day, I mean, that's not something that we typically think in. When you're traveling someplace, what are you usually thinking? What are speed limits posted in? Miles per hour, right? So we need to convert this to miles per hour. So let's see if we can't figure out how to do that. And I know we've practiced a few things like this, but this is going to stretch our minds a little bit. Miles per day. I'm going to multiply by the number 1 in some fashion, so I get rid of units of days, and I end up with units of hours. So if I want to cancel out days, am I going to put that in the numerator or denominator?
Numerator.
The denumerator. All right, good deal. Yeah. So in the numerator, excellent. Now, one day, how many hours in a day? 24 hours. And the nice thing here is that what happens to units of day? It disappears. Boy, if you can get this idea down about multiplying by 1, you can convert any units. You can convert euros to dollars. You can convert kilometers to miles. You can convert nanometers to fathoms, or fathoms to parsecs. You can convert anything as long as you know the equivalence between two basic units. So ultimately, that means I'm going to take this number and divide it by 24, and I'll be left with units of miles per hour. Now the nice thing for us is that number is still on our calculator. If you hit the divide key, it takes your previous answer and says, okay, what do you want next? Oh, divide by 24, you got it. 2,291 miles per hour. Call it 2292. Nice. Okay. Looking good on that one. Nice. Let's keep going. I lost it. There we go. Let's scroll down. I do a lot of biking. I mean, a serious amount of biking. So I kind of like this one, and it puts me in mind of one of the guys I cycle with. If you go out near Cranbrook Institute of Science off of Woodward, there's a hill that goes right down Cranbrook. And this lunatic that I ride with tries to break 50 miles an hour on his bike going down the hill, which is not bad, but the problem is at the bottom of the hill, there's a hidden driveway. And I'm always nervous that somebody's just going to pull out right at the wrong time, man. Oof. So you go first. It's okay. Après vous. Anyways, let's take a look at this one. The diameter of each wheel of a bicycle is 26 inches. So let's write that down here. This is problem number 105. So the diameter is 26 inches. That sounds like my bike so far. If you're traveling at a speed of 35 miles per hour on this bike, now what information are they giving you there? They're giving you the linear speed, right? So they're giving you the V or the nu, depending on how closely you want to write this. But it's nu equals 35 mi per hour. So the question is, well, how fast are the wheels rotating? All right. It says, through how many revolutions per minute are the wheels turning? Okay. Well, the good news is that we don't have to go very far to get at least a beginning of an answer. Omega is the only thing in this formula we don't know. Of course, we can only solve for one unknown. So I am going to run into a little bit of a problem here. V equals R times omega. But I don't have R, do I? What do I have instead? I've got the diameter. Well, how's the radius compared to the diameter? Divide by 2. Yes, thank you. So let's divide by 2. So that gives me R is 13 inches. Okay, but here's where I'm going to run into a problem. If I stick with things now, I'm going to end up with units of miles and inches mixed up. I got to pick one of these. You got to go with one of them. Now let's look back at the problem for just a second, see if we can get some guidance. It says, through how many revolutions per minute are the wheels of the car turning? So, okay. We got to work with miles per hour and turn it into inches per minute first. So that way the units there are going to match the units that we've got and the units that we want. So let's work with that unit of 35 miles per hour and see what we can do to turn it into inches per minute. So 35 miles per hour. Now, I guess the first thing I'll do is I'm going to want to get rid of units of hours and replace it with units of minutes. So I'm going to put units of hours up top, 1 hour. And 1 hour is going to get replaced by 60 minutes. Okay, so I got the first problem done. I'm getting rid of units of hours and turning it into units of minutes. The other problem, I'm going to do this all at once. Make it just one quick calculation. I want to get rid of units of miles and end up with units of inches. And that's going to be a little bit more work here for us. So I'm going to help you out. And this is trivia that I would not expect you to know on an exam or something like that. I expect you to know that there's 24 hours a day and 60 minutes an hour, but the number of feet in a mile, unless you jog a lot or something like that, probably don't know that. I'll throw it out there though. Does anyone know how many feet in a mile? 5,280. Yep. Well done. Thank you, gentlemen. So 1 mile, and notice units of miles have to go in the denominator, is 5,280 feet. And this is the units of feet now. It's not units of minutes. Like I said, don't shoot the messenger. I don't know who was thinking what when they did this. Of course, if we were on metric system like, I don't know, every other country in the world except Liberia, then this wouldn't be a problem. But, oh well. Now, we're still left with one little problem. We got units of feet, but I eventually want units of inches. So the last thing I got to do is I got to get rid of units of feet. What's the conversion between feet and inches? 12, yeah, a natural number, right? 12, because we got 12 fingers and 12 toes, right? All right, whatever. So let's see. What's going to go where? Well done. Feet at the bottom and inches at the top. So if you're keeping track of things, all our units cancel like we want them to. Units of hours cancels. So that's good. Units of miles cancels. So that's good. And then units of feet will also cancel. And what are we going to be left with? We're going to be left with units of minutes and inches. So it's going to be kind of strange, but that's what we're going to be left with. So let's see what that's going to be. Eventually what I want to do is I want to take 35 times 5,200 and 80 times 12 divided by 60. So we'll do all that on a calculator. Let's clear all this out. So 35 times 5,280 times 12 divided by 60. Oh, worked out nice and even. Isn't that special? So 39,900, no, excuse me, 36,960. 36,960. And that's going to be in inches per minute. (60 inches per minute). And let me slide back over to here. Beautiful. So that's our nu, or our V. Probably easier to think of it as V. Now I can work on calculating omega. So let's take a look here. I know what V is. I know what R is. So it's going to be 36,960 equals 13 times omega. So, okay. That's just a quick little division problem. Let's take that number that should be on our calculator and hit the divide key. Divide by 13. And I get 2,843. Wow, that sounds like a lot. So 2,843. 0.08 equals omega. Now that's how fast it's turning every minute, through what angle it turns every minute. But it's hard to fathom that in radians, right? Because that's what it is in right now. It's in radians. So, so this is in radians per minute. But that's not actually what the problem asked for, is it? Probably wanted revolutions per minute. So we're going to have to go back and think a little bit. Well, what's revolution? How does a revolution compare to a radian? And we did that. One revolution is 2 pi radians. So if I want to convert this to the answer that they need, I've got to do one last little conversion. I've got to take 2843.08, and that's in radians per minute, and multiply it by 1 revolution over 2 pi radians. So basically, I need to divide this by 2 pi, and that'll get me revolutions per minute. And that's seemingly going to be a little bit more reasonable. So if I divide this by 2 pi, you got to be careful. You can divide by 2 and then pi in parentheses. Because if I did it without parentheses, it would take your answer divided by 2 and then multiply it by pi. Your calculator's not that smart. So there we go. Basically about 452 revolutions per minute. Wow, that's a lot. And just out of curiosity, divide that by 60. So 7.5 revolutions per second is what it would be. But they wanted in revolutions per minute, so there it is. 452 call it 5 revolutions per minute. 452.5 revolutions per minute. Whew, nice. Done with that one. All right, so comments on that one. Other than that one was tough, and you're relieved to hear that I put no more than 8 or 9 of them on an exam. All right. All right, I am kidding. Yes, I am kidding. Let's see.
Like that actually going to be in the exam?
You know, it's probably a month or so before I start thinking about the exam, but I'll be honest, I have put ones just like this one on old exams. Yeah, I could easily look up in my old files and see one just like it on old exams. Now, with respect to some of these problems, look, some of them I know are tough. And I'll put a few there because we cover them in class or things I want you to know. But I'm not going to make up the whole exam with these kinds of problems. There's going to be plenty of problems that if you want to pass this class, these are the kind of bread and butter problems that I think you should be able to solve. You'll be able to pass it. There'll be problems kind of like some of the earlier stuff that we did with this stuff. Maybe an arc length kind of problem. You know, a nice simple one where basically I'm testing, are you converting to radians first? I mean, that's really the only thing you can make a mistake on there. Same thing with the area problems. Some other problems, converting degrees, minutes, and seconds to degrees, that kind of thing. So there's going to be a lot of other bread and butter type problems that you can do well on, even if you don't get some of the more challenging problems. So don't get defeated by like one or two really difficult problems. I mean, yeah, there are going to be some challenging problems there on the exam, but it's not going to be the majority. You can do well, even if you can't get every single problem. Here and then here.
Do you do study guides, or is it just mostly from textbooks?
That's a good question. I'll have something for you. In one form or another, I'll have some guidance. But as I go along, I do the problems in class that I want you to be able to do on a test. And, some of the harder problems I'll do more of, or some of the problems that I really want you to know, like converting degrees to radians or radians to degrees. I mean, those are easy problems that I hope you get. And, like earlier I spelled out that, I want you to be able to do one like this. And that, or excuse me, not this one. Where is it? Yeah. This one. I said, yeah, this would be a good problem. Convert 3 to degrees. And I'm telling you right here and now what people do. They always want to put in a pi here. Even though there's no pi as part of the problem, people put in a pi. Well, okay. But, at least I'm giving you a chance. I'm telling you now what to expect. So if you're paying good attention in class, taking good notes, you should really have a good idea of what the exam should be. I don't look at my graduate textbooks and say, hey, I'll give them this one, all right? I give them the stuff that you practice in class. That's what I emphasize. That's what I want you to know. Yes?
Do you give partial credit?
Yes, I do give partial credit, yeah. In fact, yeah, absolutely. If you make a small mistake, like maybe you're thinking, oh, it's 14 inches per mile or something like that, and you put the wrong unit in there, yeah, I'll look through and give you partial credit, sure. Yeah, I try and be pretty fair about that. So one of the things that helps me out is if you show me your work. Because if I don't see any work, how can I give you partial credit? And the other thing about showing you work is this. Sometimes you can do the wrong thing and get the right answer. Like this one. 64 divided by 16. Oh, I'll cancel the 6's. Hey, I got the right answer. Well, yeah, you did, but I'm not going to give you credit for that. Whereas if somebody made another kind of mistake, you might get almost all the credit, even though you got the answer wrong. But it comes down to you have to show me your work. It helps out both of us. It really does. All right. Do you want to do one more with linear and angular velocity?
Yes.
Just one more. Yeah, it's kind of like, well, yeah, I guess so, yes. Like or want is a strong word, right? We will do one more. Maybe you don't really want to, but let's take a look at problem number 106. So I'll look at it here for us, and then we'll finish this section up with this problem. The radius of each wheel of a car is 15 inches. So let's write that down to begin with. This is problem number 106. R equals 15 inches. If the wheels are turning at a rate of 3 revolutions per second. So what are they giving you there? Are they giving you omega, or are they giving you nu? Are they giving you W, or are they giving you V? Yeah, they're giving you omega is 3 revolutions per second. Sounds like the car is going pretty slow. I wouldn't want to be stuck behind him on I-75. He wouldn't last in this town's traffic. All right. How fast is the car moving? Yeah, not fast enough for me to be behind him, but that's a different story. There's one thing I got to correct before we really even get going on this problem. You can't just plug it in and say, oh, yeah, hey, we got this, right? V equals R times W. You can't plug it in yet. Yes. This has to be in radians per second, not revolutions per second. Revolutions per second is pretty close, but it's not the same thing. So 1 revolution is 2 pi radians. So if I wanted to convert this, I'd multiply by 2 pi is 1 revolution. That's a little bit better. And it gives me 6 pi per second. And that makes sense. That's 3 revolutions. For Shaun White in the Olympics, that'd be a 1080. They actually did some 1440s with just 4 revolutions. I just can't imagine that on a snowboard. That's insane. In any case, now we're in good shape. Let's see. So plugging that in, that's going to be 15 times 6 pi per second, which is going to be 90 pi per second. I don't think that that's what they want here. So, okay. But let's take a look back at the problem and see if we can't figure out what units we should end up with. Express your answer as inches per second and miles per hour. Okay. Well, we're done with the first part because this is in inches. So this is in inches per second. So 90 pi. I don't know. We can figure that out real quick. Let's clear out all this stuff. Yes, clear. So 90 pi. 282.74. So 282.74, and that's going to be inches per second. It doesn't sound terribly fast. Let's see here. Let's begin the work of converting that. We want to convert that to, where is it? Miles per hour. So this could be like a second part. And this part, look, I understand it gets a little tougher, but we've done this a lot today, so I'm hoping you're getting better at it. And that's going to be, V is 282.74 inches per second. Let's work with converting inches to miles first. So for myself, I'm going to work through the units of feet first. So I know that 1 foot has 12 inches. Okay. And so once I've got that, then I want to get rid of units of feet and end up with units of miles. So where's feet going to be? In the numerator or denominator if I want to get rid of it? Denominator. So 5,280 feet is 1 mile. So this is what I got to multiply by to get rid of units of inches and end up with units of miles. But now I also want to get rid of units of seconds and end up with units of hours. So let me help you out here. You could do this in 2 steps. Convert from seconds to minutes and then minutes to hours. But let me help you out. There's 3,600 seconds in 1 hour. So there you go. Now everything cancels out like it's supposed to. Units of inches cancels. Units of feet cancels. And then, last but not least, units of seconds will cancel. And what we'll be left with is units of miles per hour. So that's a way you can kind of double check yourself. If you're actually taking the time to write down the units, you can see that you got this set up right. So I want to take my answer, multiply by 3,600, and then divide by the product of 12 times 5,280. So I'll take this times 3,600 divided by, and you need parentheses here, parentheses 12 times 5,280. There you go. 16 miles an hour. Like I said, I don't think I want to be behind him as he's driving on 696. But there's your answer. 16.06. In the numerator, you're left with the units of miles. In the denominator, you're left with units of hours. MI per hour. Beautiful. Beautiful. Comments or thoughts on that one? Alrighty. Let's take a break.